Okay, my name is Jouni Honkola, and I have been working for AFRY now 15, 16 years, and focusing on during my career for the industrial investments. I have been in different positions in different industrial sectors: mining, metals, pulp and paper, chemicals, during my whole career. And the past 12 last years, I have focused only on the mining sector investment or mining and metal sector investments. And today I'm going to present you something to think, and maybe let's say the changes what has been happened in these 12 years even with the mining sector development phase. And the reason for that is mostly in the permitting point of view, and on the investor's point of view, it's question about the permitting risk point of view. So I have 15 minutes time, and I will start my watch. Sorry, yes, I'm the project guy, so I would like to keep my schedule. I'm going to present you the one, let's say, the theoretical way forward when or for the investment development phase, and it's called gate theory. And the gate theory in the big means that the project will be developed or investment will be developed step by step ahead. And idea with this is that money will be injected to the investment only for the, let's say, to go ahead one step ahead. And in case in some of these gates it will be seen that this investment is not viable, or there is something that profitability cannot be reached, investment development can be closed early enough not to spend too much money for the investment development. And we have seen also in the world investments which have been implemented even, and then it's typically always question about the hundreds of millions of euros, and it's quite, let's say, the difficult situation in case you have developed and implemented your investment, and you realize at the start of the production that this production will not be ever profitable. So idea with the gate theory is that investment development can be stopped in case the plan is not viable. So in our mindset, we would like to continue with the three separate, let's say, the main study phases: pre-feasibility study, feasibility study, and definitive feasibility study. And you can see here approximate. This is now only an example and average something these time schedules, but the typically pre-feasibility study for the greenfield mine investment, for example, will take 1 year when it's done properly. Feasibility study most probably take at least 1 year, and definitive feasibility study definitely will take 1 year. 1 year to be developed to the stage where it should be when the decision of the final investment decision will be made. Then idea is to start, of course, with the mining investments from the scoping study, and these are, let's say, the high level studied or prospecting, for example, has been done a long time, couple of years maybe, or many years ago before starting the PEA, and the idea is to develop capex, opex, and profitability calculations to the level of plus minus 50% level, accuracy level, and this means that it's quite high level study, not very technically. Let's say the technologies are not developed in very details. It's based on the general knowledge of the whatever production it is, and the mineral resource estimate will be developed during the PEA. Land use planning process is taking today in Finland very long time, so the land use plan, in case it's needed, should be started in the PEA, and the baseline studies at least at this stage, baseline studies, and with the baseline studies, I mean environmental studies, environmental baseline studies, this is the latest time to start those. It looks to be so that those might be needed in the greenfield project, might be needed to start even a couple of years earlier. And in case findings in the PEA is positive, project team will develop report to the gate, and the decision maker in the gate decide that, okay, it looks to be quite good business. It looks to be profitable in this accuracy level. Let's go ahead. Let's do the pre-feasibility study. And in the pre-feasibility study, all reserves and mine plan are started to be developed further. Then idea is to compare several production options, and this means that the money or the ore body in the ground is not profitable for anyone before it's concentrated to some kind of form, and technical team, process team should start to develop these production options and compare those which one is maybe the best one, and the idea is to select only a couple of to the further study phase, because you can't study, let's say, the 5 or 10 several different production options quite long time ago. It will be money spending or too much. It will cost too much to develop too many production options. And once again, findings will be presented in the report, and the EIA must be started at the beginning of pre-feasibility study. And in this example, EIA will take 18 months, and it's quite, let's say, some kind of average time what EIA at least takes, because baseline studies must be based on the 1 year seasons, so the summer, autumn, winter, and springtime fauna and flora have to be and must be studied and reported. So it's time, at the beginning of pre-feasibility study, it's time to start EIA, environmental impact assessment. And here you can see in the right corner box the schedule, what kind of activities there are when you prepare the EIA, and the end of the EIA process is conclusions, EIA conclusions given by the authorities in ELY-keskus. So the ELY-keskus is Center for Economical Development, Transport and the Environment. So EIA will end to that point, and in case findings are still viable, once again we go to the gate, request from the owners or the decision makers that shall we continue, or do you give us permit to continue to the feasibility study? In case yes, we start feasibility study. And feasibility study is the stage where the process will be developed even further and do the basic engineering level. It's called in the engineering world basic engineering. So the process solution more or less must be developed to the basic engineering level, because environmental permitting needs to have that technological information about, and at least for the pollutions. And with the pollutions, I mean pollutions to the air, water, and noise. And so the process will be developed to the basic engineering level. Other disciplines like civil, plant design, electrical design, automation design to the pre-engineering level. Once again, the CapEx, OpEx, and the profitability calculations will be prepared, and implementation method where the CapEx is based on is first time defined in the study report, and the mine permit application must be started at this stage. And why it's only in this stage? You can't apply mine permit without EIA conclusions from the ELY-keskus. So these are connected together, these two permits. Once again, report will be written, and the project team will go to the gate and request, shall we continue? And typically, this is the stage when the capex, opex, and profitability calculations are in the level of plus minus 20%. So it's time to do the investment proposal or preliminary investment decision. And why so? No, well, reason is that because of during the definitive feasibility study, financial package will be collected together. So in case at this stage this investment seems to be profitable and it's viable, then decision makers gives us a permit to continue to the DFS, and at the same time environmental permit will be applied from the AFRY, and the AFRY is regional state administrative agencies, so aluehallintovirasto in Finnish. Process solutions will be developed during the DFS in the quite detailed level already. Because of environmental permit application should include very detailed level information about the process and as I told you, pollutions, and also for the financing the investment capex, opex, and profitability calculations must be in a quite, let's say, the low upgrade level. So we call it like plus minus 10% level, and final implementation method will be defined during the DFS. Main contractors, vendors will be selected during the DFS. So all the main contracts like construction contracts, process solution supply, automation system supply, electrical system supply has been developed to the basic engineering level and agreed on the contract level already with the suppliers, which one it's ideal then to continue to the implementation. And once again, it's time to write the final report and go to the gate and request permit to continue to the implementation. And at this stage, also all the permits should be granted. And typically, it is possible to have environmental permit from the AFRY in this time, 23 months. So your investment would be in the very good level of the technical knowledge, and the permit will be granted by the AFRY, aluehallintovirasto. But the problem then is that there is appeals. And in Finland, I have not seen past 5 years any mine investments, or let's say the mine investment where the environmental permit has been applied and approved by the aluehallintovirasto, that those will not be appealed. There will be appeal process, and in Finland it goes like appeal first to administrative court, which takes today 1 year, and depending on the findings or let's say the decisions of the administrative court, someone most probably will appeal to the Supreme Administrative Court also, and it will take also 1 year. Difficulty today in Finland is that your project organization and the investment on the otherwise would be ready to go ahead with the full power, just to do the decision, okay, go ahead, but you need to do this start with your own risk in case you get even permit to start that with your own risk, because of this environmental permit appeals. And today we have seen a couple of examples that different court level has changed aluehallintoviranomaisen decisions. So the AFRY decisions has been changed, and there will be quite big difficulties with the investment in case you are, for example, in the startup phase of the production, as we have one investment in Finland at the moment, but there would be huge changes for the environmental permit. That's my message today, and Päivi will tell you more about this environmental permit process in much more details. She's expert on that, and Emily will tell you about the ore reserves and the mining a little bit more. Thank you. This is what I have today to tell you, and in case there's any questions, please ask.
So Päivi Piken is my name. I work at AFRY in a department called Mining Environment, and my working area is geochemistry and environmental risk management. Today's topic is about systematic management of environmental and social project risks. And the focus is in the integration of the technical design and the environmental assessments. And we need to look into how all this will contribute to the de-risking of the project in general. I start with some classical quotes that unfortunately are still commonly heard. The first bubble here is about thinking that our limits are the permit limits, that we are fine as long as we sort of cope with all of these issues that are defined in a permit. But we have to keep in mind that the environmental permit isn't, it doesn't cover everything that could ever happen. So the polluter pays principle is still very strong in legislation everywhere in Europe. And in practice, that means that, let's say, even if you don't have, or almost nobody has permit limits for, let's say, lanthanum or something quite unusual, it doesn't mean that you are allowed to pollute with that either. If you cause a damage with something that wasn't defined in your environmental permit, you're still responsible and it's still part of your project risks. The stakeholder issue is always in top 5 or 10 in the mining risks. The common mistake is to think that it's enough if you speak to your municipality leaders or some other leaders. They seldom represent the whole range of opinions that is out there. Another common mistake is to think that there's a lot of empty space there. It doesn't look like there's much going on at all in the area when you're looking at the map. But there is no such thing as empty space. All area is always in some use. You always damaging somebody else's interests when you go and start working with the mining project. A common mistake is also to think that environmental assessments are only needed for the permitting, or that the environmental work wouldn't need special management or special planning. And sadly, we constantly still hear the thing that we just need to get the environmental permit early and quickly, and that's it. And this is a typical conversation that takes place a few years before the project is buried and forgotten, because you're not going to get anywhere with these attitudes. So therefore, luckily, we're moving to better direction. And now we're going to discuss a bit the what is the foundation for a good project then. To gain that permit that everyone wants, we have to turn our focus away from the permitting. Focusing to the permitting doesn't help you to get the permit. So let's look into this different way around. The environmental and social assessments are not done for permitting. Environmental and social assessments, they are done for technical design, to support technical design. And it's the technical design that technically is the thing you need for the permitting. I'm saying this because there's no such thing as environmental permit for a site or environmental permit for a project. The environmental permit is issued for one specific technical plan, one specific technical design, or the overall design of the project. If that plan, if that design changes, the environmental permit has no longer value. How this thing then should work? There's you start from identification of environmental and social risks. They are always site-specific, and based on these risks, you think of the best available technologies, how to mitigate these risks, and make the first technical designs for the place. And as Jouni already explained, you have to have a technical design to assess environmental impacts. Giving a bit more example is that, for example, if you're depositing tailings, you need to know whether you have wet tailings or dry stack tailings or something between, or if you, what are your basal structures, what are your dam structures like, what kind of saturation circumstances there will be in the facility. Even if you have exactly same process, exactly similar looking tailings, but you change your structures or dimensions of the facility, your water quality will change. You can't assess without having the technical design. You can't assess anything. So you need to have a technical design before you can go assessing impacts and before you can assess the relict risks. It often happens that the first design proves not to be yet good enough, even if you try to apply everything best possible technology that is available or what usually would work for rather similar cases. You may, for example, have still too high impact on the local water course. The tolerance of the water course is exceeded simply. Then the thing goes back to the drawing table and the plans are a bit improved. Then you go back to the assessment of impacts and perhaps in the next round it actually works. Then you can accept the technical design, then you can lock the technical design, then you can go to the permitting. This system often takes very long time, and these different loops are distributed over several study phases, and that's fine. And that is the nature of the planning. That from pre-feasibility study to feasibility study, you keep improving. And going back to the correct point of focus. So the focus has to be in the risk management, in the environmental and social project risk management. And it starts from the identification of site-specific issues and risks. There's no standard range of issues. Your site may always be the first one ever in your own country that has certain specific type of environmental problem or impact. So never apply only standard ranges. It's always to be assessed very, very site specifically. The next step is to recognize what are the big issues. What is a thing that could be a project killer? We prioritize the high risk issues and put more effort to working with those issues. The next work steps are all about the systematic reduction of uncertainties. The bigger the risk is, the smaller the allowed uncertainty is. And going back to the correct point of focus, this is a bit, the risk management has to be in focus because that's the ball in a game. Everyone knows that if you play ping pong, you have to keep your eye on the ball. If you start staring at the referee, in this case, the environmental authority, you will miss the game. So our focus point in the development phase is the risk management. Around the risk management, we can build the rest of the work. Don't even try to focus to all details of this picture. There are only a few details that I want to talk about. Jouni already explained the sequence and the roles of the different tasks here, and Emily will go more into the resource issues in his presentation. I just point out that from environmental work perspective, we have to try to work simultaneously with issues that have similar nature. For example, in EIA program stage, in the Finnish system, notice the Swedish system is very different from this. So in the EIA program stage and PEA stage, the work is a lot about identification of alternatives. In the next steps, EIA and pre-feasibility study, it's all about evaluation of alternatives. In an ideal world, EIA alternatives and the trade-off studies in a PFS are almost the same thing, or actually it's worked as one package. And when there's just one alternative left, the more detailed study starts, and then it's also a suitable phase for the environmental permit procedure. Understanding the interlinkages of different tasks is one of the biggest challenges in the project development. Environmental studies take a horrendously long time. All of them take years. It's from the first field studies to the hydrogeological model. You can't count it in months necessarily at all. Geochemistry studies take a long time. Just the sequence of kinetic testing programs and geochemical modeling, we're talking about years as well there quite often. So, and these tasks are sequential. So it's extremely important to look beyond the task at hand. At each study phase, we have to think of what are all the future uses of the data, directly or indirectly. If I'm being clever here at the sampling stage in beginning, and I think I know it all, what the others are going to need from me, what kind of parameters I have to study, how detailed this has to be, I may walk towards disaster. In that water course receptor, there may be some tiny little creature in the bottom of the river I have never even heard of, and it's extremely sensitive to something that is not in my normal parameter range. So there are many study steps that take inputs from each other, and if you here in the very end of the chain realize that we don't have some data that we needed, we missed the critical parameter, we can't do this assessment, oh no, now we can't even apply for permit. That will take us back to the beginning. At the worst case scenario, it's 2 or more years that you lose in a project schedule. Unfortunately, the whole project is full of this sort of interlinkages. There are interlinkages inside the environmental work. There's interlinkages between technical disciplines and environmental work. There are interlinkages between exploration and the environmental work, and it all has to work. Don't even try to study again in detail this picture. This is here not to explain something. This is here to be overwhelming, because that's what the management of the environmental work is like. It's a horrendous network of different things happening simultaneously, giving one input going to one place and output coming out of for the next one. And finally, there's one more thing why environmental work in a mining project needs careful planning and management, is that there are many different criteria you have to answer to. In other words, there are multiple reporting platforms. As I already told, we have to report to other disciplines, but we also have to report to the owners. They may have their own policies that set certain criteria. In feasibility studies, we report risks and costs, and the mineral resource reporting standards, for example, set the criteria what has to be reported, how the information has to be produced. National legislation and practices are regulating the permitting system and EIA. There we report plans and impacts, among other things. Then for the financial decision making, we also have to report impacts, risk and compliance to the different criteria. Here we have to assess compliance with the environmental social performance standards that the financial segment works with. And last but not least is the stakeholders. The local information expectations may differ from all the other information expectations. When we choose our methods, if we think of only one of these fields, we are likely to fail on other fronts. And there's a reason why I don't have the permitting here in the center point. If we think of the permitting, we fail to deliver to all of these other fronts, and the project is still going to fail. Therefore, having the big picture, managing the whole environmental work system, reducing the uncertainties in a structured way, that has to be in a center point. And we can deliver to all of these reporting platforms, and one of them is the permitting. And as the last overhead, I'm not going to speak anymore about this, but this is hopefully your conversation in the end of your project development phase. You took these points to consideration and it all went well, and this is what your discussion will be like. Thank you.
So, hello everyone. My name is Emeli Rantala and I'm a senior geologist at AFRY, Norway. And I have 13 years of international experience in exploration and mining industry. And I'm going to talk about the best practices in geological modeling, and when the goal is to make a best possible mineral resource estimation. And today I'm going to go through data collection, common sources of error, why it's important to model geology in 3D, and what to consider when building a 3D model for mineral resource estimation. Sorry, jumped a little. But yeah, data is the basis of all geological models, and it's impossible to build a good model with bad quality data. Unfortunately, it's still very possible to make a bad model out of very good quality data. And it's important to start collecting the data properly right at the start of the project. But it's quite common that companies are collecting only the data that is needed at that moment, and they are not really thinking what will be needed in the future. For example, it's common that many projects, they don't have enough density information when it's time to do a mineral resource estimation. Also, it's relatively common that rock quality information and metallurgical data is overlooked and not collected really until it's urgently needed. It also needs to be evaluated whether the sample population size, quality, and spatial distribution of data are adequate to determine the variability and distribution of the mineralization at that level that is needed for mineral resource estimation. And there should also be a good understanding of what kind of information is needed and for what purpose it will be used for. And common sources of error and procedural errors. And this can happen when data is recorded inconsistently. For example, when there's multiple data collectors collecting the data differently. And core logging is one example of this. And instrumental errors. And that is when the instrument is not recording properly. For example, the downhole survey tools. And coordinates can be messed up by faulty GPSs, or if there's something wrong with the lab instruments, assays can come back with inaccurate results. Human errors. People make mistakes. For example, when handling data or when operating instruments. And all data can't be expected to be at equal quality or have equal accuracy. and this needs to be taken into consideration. For example, it's sometimes impossible to validate all historical data, but it can still be very useful and used for certain applications as long as the data limitations will be taken into account. And all these errors can affect your database and mineral resource estimation. So to minimize the errors, it's key to have standardized procedures for data collecting and handling. And all data should be quality controlled and validated. And everyone knows that good quality database is super important, but sometimes it's forgotten that the database needs to be maintained as well. And the figure, or the two figures on the screen, that's one example of quite common issue. The upper image shows a graphical drill core log, which gives the user large freedom, and it's good for interpretations. But at the same time, there's much greater chance to record the data inconsistently. And on the lower image, you can see a template where the parameters are predefined. So you have to, or the process is standardized. And why model geology in 3D? Nowadays, it's industry standard for mining and mineral exploration to model geology in 3D, and pretty much everyone does it. But what could be improved is that sometimes the modeling could be started earlier in the project. It's beneficial to have the model up and running as early as possible. Then it makes the planning easier, and updating the model will become a natural part of the work process. Also, it's important to consider for what purpose the model will be used, and therefore what the source data should be and what data is needed to make the model to match the usage. And some other reasons to model geology in 3D is that geology is quite obviously 3D geometrical science, and rock properties and rock behavior is a 3D problem. And it's best to visualize geology in 3D. And interpretation is also much easier when you can have all multidisciplinary data combined in one platform and then interpret it all together. There's the example image on the screen, the left one. You can see that there's multiple different data sets used. And then when you use all the different data types together for the interpretation, you can get a better interpretation. And in general, you should not look at the geological data as a point data, but understand the 3D aspect of the geological features. And all the interpretations that have been made, they must make sense also in 3D. And geological 3D modeling for mineral resource estimation. The goal is to have geologically sound model that honors the data and controls on the mineralization. And all geological data should be considered and used for the model. unless there is some very good reason not to. And in that case, it needs to be explained with good reasons and why some data are excluded from the model. And the data needs to support the model, and the model needs to match the geological observations. And the modeler needs to understand the relationship between the mineralization and the geological processes that resulted in its spatial distribution and geometry. For this, it's important to understand the applicable mineral deposit models and the character of the mineralization for the deposit. And if the modeling is done by someone who is not working with the deposit daily, it's important to have a dialogue with some individuals who have direct personal knowledge of the deposit. And structural data is, in many projects, it's not measured at the needed quantities or quality. And on the figure that is on the screen now, it's a good example how structural measurements have been used to make a geologically accurate model. And in this example, there's the two different wireframes, yellow and blue, and they each represent different metals. And as you can see from the shapes of the wireframes, the structural measurements were used to make the model match the actual geological observations, the structural measurements. And the model would look very different if it would have been modeled solely based on grade. And that would result in less accurate model, less realistic model, and therefore also the mineral resource estimation would be less accurate. So in the end, the geological interpretation is still the fundamental skill that you need. And some key takeaways. So you need good quality database, solid database interpretation, and geologically true 3D model to make accurate mineral resource estimation. And thank you.